Tonight, we're going to speak about chaos. Not chaos as a loud mess, not chaos as panic, but chaos as a quiet property of certain systems, a kind of sensitivity woven into the fabric of motion. In a calm room, the word chaos can sound harsher than it really is, so let's soften it from the beginning. In science, chaos often means this: two things can start almost the same and still end up different, not because anything supernatural intervened, not because the universe changes its mind, but because the system amplifies tiny differences over time. And that amplification can be so steady and so relentless that after a while, prediction becomes less about intelligence and more about limits. It is a humbling idea, and in a strange way, a comforting one, because it tells you that uncertainty is not always a failure of attention. Sometimes uncertainty is a built-in feature of reality. Now, the title of this episode is Web of Chaos, and that is deliberate. We'll talk about chaos in the mathematics of motion, but we'll also talk about the cosmic web, the vast structure of the universe on the largest scales, a network of filaments and voids shaped by gravity. And we'll ask how these two webs relate. Is the cosmic web chaotic? In what sense? And what does it mean for the future of structure, for our models, and for our quiet human desire to forecast? To keep this sleep-friendly, we won't rush. We'll build slowly. We'll begin with a simple grounding story, how chaos entered modern scientific imagination. Then we'll move to the sky, from the orbits of planets to the stirring of gas to the growth of galaxies. We'll talk about the cosmic web as an emergent pattern, order appearing from instability. And we'll end with a gentle thought that even when systems are chaotic, they can still be lawful. That may be the most soothing part of all. So first, a small history. For centuries, physics had a reputation for certainty. If you know the forces and you know the starting conditions, you can calculate the future. That idea became an emblem of classical mechanics. It worked beautifully for many problems: the arc of a cannonball, the swing of a pendulum, the orbit of a planet around the sun. But then researchers began to notice something. When systems have three or more interacting bodies, or when they are non-linear in certain ways, prediction becomes fragile. The equations still exist, the laws still apply, but tiny uncertainties in measurement, in initial conditions, can grow until a long-term forecast becomes unreliable. One famous doorway into modern chaos theory came from weather. A scientist running a simplified weather model discovered that rounding a number, changing a value by a fraction, almost nothing, could produce a radically different long-term outcome. This was not because the computer was broken. It was because the atmosphere is a system that mixes and amplifies. A whisper becomes a wave. That discovery eventually became popularized as the butterfly effect, an image that suggests that a small disturbance can ripple outward, changing outcomes far away. Now, the butterfly image can be misleading if taken literally, but the underlying point is real. In certain systems, small differences matter, and they matter more as time goes on. If you're listening at night, you can take this idea gently. Think of a river. At the source, the flow might look simple: a small stream, clear,
narrow. Farther downstream, it becomes more complex. It meets rocks, branches, bends. It splits into eddies. It becomes turbulent. The water obeys physical laws at every point, and yet the detailed pattern of motion becomes difficult to predict. Not because the river is lawless, because the river is sensitive. Chaos is that sensitivity made mathematical. Now, let's bring this into space. It may feel like the heavens should be the opposite of chaos. Space is quiet. Vacuum is clean. Gravity is simple. But gravity has a particular property. It is long range, and it couples everything to everything else, at least in principle. And when you have many bodies pulling on one another, you can create a system that is deterministic, lawful, and still unpredictable in detail. This is where the web metaphor becomes useful. Chaos is not random, it is structured unpredictability. And the cosmic web is not chaos, it is structured matter. But both can be described as patterns emerging from many interactions repeated over time. To begin that connection, we'll start in the most familiar place, our own solar system. Because even here, in the neat clockwork you see in textbooks, there are subtle hints of chaos living quietly under the surface. If you are still awake, consider this as a light question. When you picture the solar system, do you picture perfect predictability, or do you leave room for gentle uncertainty? You can answer in your own mind, or you can tell me in the comments what your intuition says. Now, let's drift into the first kind of cosmic chaos, the long-term stability of orbits. If you are still awake, consider this as a light question.
In the solar system, most of our predictions are extremely good. We can compute eclipses centuries in advance. We can navigate spacecraft with astonishing precision. We can describe orbital periods with elegant mathematics. And yet, if you extend the time horizon far enough, the picture becomes softer. The reason is not that the sun and planets are unreliable. The reason is that the solar system is not a two-body problem. Every planet tugs on every other planet. The tugs are small, but they are persistent. Over millions of years, small effects accumulate. This is where chaos can enter. If you imagine two nearly identical solar systems, same masses, same positions, same velocities, but with a difference so tiny you could never measure it, those systems can diverge over very long times. Not immediately, not dramatically, but gradually, until after tens of millions of years, the detailed orbital angles can become effectively unpredictable. This does not mean planets suddenly fly away. It means that certain aspects of the motion lose forecastability. In chaos theory, one way to describe this is through a timescale called the Lyapunov time, the time over which small differences grow by a large factor. For the inner solar system, this timescale is on the order of millions of years. That number can feel huge, and it is. For human life, it is eternal. For the age of the solar system, it is a small fraction. So the solar system is both stable and chaotic, depending on how you define stability. Stable in the sense that the architecture persists for billions of years. Chaotic in the sense that detailed predictability decays over long times. This is already a useful emotional lesson. A system can be reliable without being perfectly predictable.
Now, when astronomers explore orbital chaos, they often do it through simulations. They integrate the equations of motion forward in time, changing initial conditions slightly and watching how the outcomes spread. The most common result is not catastrophe. The most common result is gentle divergence in phase, the details of angles and timing. But sometimes rare paths appear, resonances shift, eccentricities grow, orbits become more elongated. In extreme cases, instabilities can occur. The word resonance matters here, and we can define it softly. Resonance is when orbital periods relate in simple ratios, like 2 to 1 or 3 to 2, so that gravitational nudges happen repeatedly at similar phases. Resonances can stabilize or destabilize, depending on context. They can lock systems into patterns, or they can pump energy into certain motions. In the asteroid belt, resonances with Jupiter carve gaps. In exoplanet systems, resonances can create beautifully ordered chains. But resonances can also be gateways to chaos when multiple resonances overlap. This is one reason exoplanet systems can feel surprising. Some are extraordinarily compact. Some are tightly packed in resonant sequences. Some appear delicately balanced, like a set of coins stacked on edge. And yet they survive. Nature does not avoid the edge of instability. Nature explores it. Now we can widen the frame. Chaos in orbital dynamics is not only a curiosity for our solar system, it has become central to understanding planet formation. Early planetary systems are crowded. Young planets migrate through disks. Planetesimals collide and scatter. Moons form and rearrange. This is not tidy. It is a gravitational conversation with many voices. Over time, the system relaxes into a more stable configuration. Some bodies are ejected, some collide and merge, some settle into resonances. So if you ever wondered why the solar system looks relatively orderly, one answer is this: it may be the survivor of an earlier, more chaotic epoch. And that brings us to the next step. If gravity can create chaos in the motion of a few planets, what happens when gravity acts on billions of particles, on the dark matter and gas that fill the universe? That is where the cosmic web enters. But before we go that far, it helps to introduce one more gentle concept: nonlinear growth. In many systems, a small push produces a small response. That's linear. In nonlinear systems, a small push can produce a response that changes the system's ability to respond, amplifying or saturating, feeding back into itself. Gravity, in a universe with expanding space, produces a kind of nonlinear growth in density. Slightly denser regions attract more matter, which makes them denser still. This is not chaos exactly, it is instability. But instability is the soil from which chaotic behavior can grow. So now we can transition. We will move from the elegant orbits of planets to a much larger stage, the early universe, where tiny fluctuations grew into a web of structure. If you're still awake, here's a simple question before we continue. Do you find it calming or unsettling that the solar system can be lawful and still not perfectly predictable? Let me know in the comments. Now, let's go outward into the largest scale patterns that gravity can build.
To understand the cosmic web, we begin with something very small. Not a galaxy, not a star, a fluctuation. In the early universe, matter and radiation were distributed almost uniformly. Almost. There were tiny variations in density. slightly denser patches, and slightly less dense patches. These variations were small enough that, at first, they were simply gentle ripples. But gravity does not ignore a ripple. If a region is slightly denser, it pulls a little more strongly. It draws in more matter. As it draws in more matter, it becomes denser. This is gravitational instability. The important thing is that the initial differences were tiny. The growth over cosmic time was enormous. This process is one of the great narratives of cosmology. How simple beginnings produce complex outcomes. Now, where does Webb come from? When you simulate the universe on large scales, especially the dark matter, which dominates the mass budget, you see matter arrange itself into a network. Dense nodes connected by long filaments. Between them, large underdense regions, voids. If you could float above it, it would resemble a foam or a net stretched across hundreds of millions of light years. This is the cosmic web. And it is not a metaphor only. We see it in galaxy surveys. We map it through the distribution of galaxies. We infer it through gravitational lensing. We see hints of it in the intergalactic medium, diffuse gas tracing filaments. The cosmic web is a real structure, emerging from gravity acting on initial fluctuations. Now, is this web chaotic? The web looks complex, but complexity is not the same as chaos. A snowflake is complex. A fern is complex. A coastline is complex. But chaos is a specific kind of unpredictability within deterministic rules. So we should ask more carefully, what aspects of the cosmic web are sensitive and what aspects are robust? One robust aspect is statistical. If you start with the same kind of initial fluctuations, with the same power spectrum, the same overall rules, the universe will produce a cosmic web. It may not be identical in detail, but the statistics will match. Filaments will form. Voids will form. Clusters will form. In that sense, the cosmic web is predictable. Another robust aspect is hierarchy. Small structures form first. Then they merge into larger structures. This is called hierarchical clustering. Again, predictable. But the detailed placement of specific galaxies, the exact shape of a particular filament, the precise merging history of one cluster, those details can be sensitive. If you change the initial conditions slightly, those details can change. Not because the laws change, because gravity amplifies. To see this, cosmologists run n-body simulations, computational universes where particles represent chunks of dark matter. They start with initial conditions inferred from observations. They let gravity evolve the system as the universe expands. When you look at two simulations with nearly identical starting points, you often see that large-scale statistical properties are similar, but small-scale details diverge. The location of a specific substructure, the timing of a merger, the internal arrangement of a halo, these can differ. This resembles a kind of chaos, sensitivity in detail, stability in statistics. Now, there is a quiet beauty in that. It means the universe can be both predictable enough to model and varied enough to be endlessly detailed. The cosmic web is not random. It has structure. But it is not a crystalline lattice either. It has freedom.
If you want an analogy, think of clouds. Given a certain temperature and humidity profile, you can predict that clouds will form. You can even predict general types: layered clouds, towering clouds, thin wisps. But you cannot predict the exact shape of every curl and gap far into the future, because the atmosphere is sensitive. The cosmic web is similar, but slower. It is weather on cosmic timescales. Now, we can ask something more subtle. In chaotic systems, there is often a boundary between predictability and unpredictability, depending on scale. On large scales, the universe is smooth. On intermediate scales, it is web-like. On small scales, it is complex. Galaxies with turbulent gas, star formation, feedback, magnetic fields, and more. So perhaps the web of chaos is not a single phenomenon. Perhaps it's layered: order on large scales, sensitivity in the mid-scales, and active chaos in the small-scale physics of gas and stars. To explore that, we need to introduce gas. Dark matter is collisionless. Its particles pass through one another. It forms structure through gravity alone. Gas is different. Gas has pressure. Gas can shock. Gas can cool. Gas can form turbulence. Gas can form stars, which then inject energy back into the gas through radiation and explosions. This is where chaos becomes more literal, because fluid turbulence is a classic chaotic phenomenon. It mixes. It cascades energy from large eddies to small eddies. It produces patterns that are lawful and still unpredictable in detail. So when we talk about the universe as a web of chaos, a big part of the story is this. The cosmic web sets the stage, and baryonic physics, the physics of normal matter, plays a complex, sensitive drama on that stage. If you're still awake, here is a gentle question. Do you think the universe is more like a clock, predictable, or more like weather, lawful but sensitive? You can answer quietly to yourself or share your thought in the comments. Now let's move one layer deeper into turbulence, star formation, and the small-scale chaos that lives inside galaxies and filaments.
Inside a galaxy, the word calm can be misleading. From far away, a spiral galaxy looks serene, a graceful disk, curved arms, a soft glow. But within that disk, gas is constantly moving. It flows along spiral arms. It compresses. It cools. It fragments. It forms molecular clouds. Within those clouds, gravity pulls inward. Stars ignite. Radiation pushes outward. Winds blow. Sometimes a massive star ends its life in a supernova, injecting energy into the surrounding medium. This cycle creates a restless environment, not violent in a cinematic way most of the time, but dynamic. And dynamics is where chaos can live. In fluid dynamics, turbulence is a classic example of deterministic unpredictability. The equations are known, but the outcomes are sensitive. Small changes can produce different eddies, different filaments, different mixing patterns. Now, the interstellar medium, the gas between stars, is not a simple fluid. It is multi-phase: cold, dense clouds, warm, diffuse gas, hot, ionized bubbles. It is threaded by magnetic fields. It is stirred by rotation, gravity, feedback, and cosmic rays. So the patterns in the gas can be complex and irregular. Yet, again, there is a calm scientific truth.
Complex does not mean meaningless. Astronomers measure turbulence statistically. They look at velocity dispersions. They look at power spectra of density fluctuations. They look at how structure changes with scale. In other words, even if the exact shape of one cloud is unpredictable, the distribution of cloud properties can be modeled. This is a recurring theme: chaos in detail, order in statistics. And that theme extends beyond galaxies, out into the cosmic web itself. Because filaments are not only made of dark matter, they also contain gas, the intergalactic medium. And that gas can flow along filaments, shock at nodes, and heat or cool depending on environment. In the modern picture, a large fraction of normal matter lives not inside galaxies, but in diffuse filaments and warm hot gas between galaxies. This gas can be hard to detect because it is thin, but it matters. It feeds galaxies, it carries metals, it holds the history of cosmic cycles. And in 2025, as instruments improve, we continue to refine our view of this cosmic weather, the flows and shocks that move matter through the web. Now, a quiet note about the word chaos again. When scientists say a system is chaotic, they do not mean it is hopeless. They mean that long-term prediction of exact states is limited. But there are many things we can still predict. We can predict the range of outcomes. We can predict typical behavior. We can predict trends. In galaxy formation, for example, we can predict that higher density regions will form more galaxies. We can predict that feedback will regulate star formation. We can predict that mergers will occur. But predicting the exact moment when one specific star forms is not the point. The point is the emergent patterns. This can also be calming because it mirrors life. You cannot predict every moment of your future, but you can predict certain trends if you care for your health, build supportive habits, and keep steady goals. The details will vary, but the overall direction can still be meaningful. The universe is similar. Its detailed microstates are complex. Its macro patterns are stable. Now, let's bring in one more scientific concept that helps bridge chaos and the cosmic web: phase space. Phase space is a way of describing a system's state, not just by position, but by momentum or velocity as well. In a chaotic system, trajectories in phase space can stretch and fold, like dough being kneaded. Stretching amplifies differences. Folding keeps the system bounded. This stretch and fold picture is a good metaphor for mixing. And mixing is at the heart of both turbulence and cosmic structure. In the cosmic web, matter streams into filaments and nodes. It collapses, it virializes, reaching a kind of dynamic equilibrium in halos, where random motions balance gravity. The motions are not simple. They are the result of many infalls and mergers. So in a halo, the distribution of particle trajectories is like a record of a complex mixing process. Again, the details are sensitive, but the statistical form, how density profiles look, how velocity dispersions behave, can be robust. This is why cosmology uses simulations as a bridge between theory and observation. Simulations are not perfect. They depend on resolution. They depend on sub-grid models for feedback. They depend on numerical schemes. But they are a laboratory. They allow us to explore how complexity emerges from simple laws. And they reveal something quietly reassuring. Even when systems are chaotic, they are not arbitrary. They are constrained by conservation laws, by energy, by momentum, by gravity's geometry. So the universe can be complicated and still disciplined. Now, let's turn towards something that feels especially web-like in the context of chaos, the idea that the cosmic web is not static. It evolves, it rearranges, filaments shift, voids expand, clusters grow. And within that evolution, there may be places where predictability fades faster than we expect. This is especially true when we include not only gravity, but feedback processes that are themselves sensitive, like when a burst of star formation triggers winds, which then alter future star formation. So, in the next file, we'll talk about feedback loops, how small changes can cascade into different galaxy histories, and how, despite that, the universe still produces recognizable populations. If you are still awake, here's a light question. Do you find the idea of order in statistics satisfying, or does it feel too abstract? Comment below with your instinct. Now, let's move into feedback, the quiet engine that can turn a small difference into a different cosmic outcome.
Feedback is one of the most important words in modern astrophysics. It means that the results of a process loop back and affect the process itself. A galaxy forms stars. Those stars emit radiation. Radiation heats and pushes gas. Gas becomes harder to collapse. Star formation slows. That is a negative feedback loop. It regulates. But feedback can also be positive. A shock compresses gas. Compression triggers star formation. New stars produce more shocks, which compress more gas. Now, the universe uses both. Feedback loops do not guarantee chaos, but they create the conditions for sensitivity. Because once you have loops, you can have amplification. Imagine two young galaxies with almost the same initial conditions. One forms a few more massive stars early on. Those stars explode as supernovae. The supernovae drive out a bit more gas. The galaxy becomes less able to form stars for a while. Its later history changes. In another case, slightly fewer early supernovae might allow gas to remain. Star formation continues. The galaxy grows differently. Over billions of years, these small differences can lead to different structures, different stellar masses, different metallicities, different morphologies. Yet, at the same time, galaxies fall into populations, spirals, ellipticals, dwarfs, star-forming or quiescent, metal-rich or metal-poor. There is variation, but also pattern. This is again the same theme: sensitivity in detail, structure in statistics. Now, in cosmology, there is a special role for dark matter. Dark matter provides the gravitational scaffolding. It forms halos. Halos merge. Halos create potential wells. Gas falls into those wells. Stars form within the gas. So, in many models, the chaotic part of galaxy evolution is partly driven by baryonic feedback, while the broad skeleton is set by dark matter structure. But even dark matter halos have sensitivity. Mergers are complex. Small differences in orbit parameters can lead to different internal structures. And when two halos merge, the timing and geometry can influence what happens to the gas, how strongly it shocks, whether a disk survives, whether a central black hole is fed, whether a burst of star formation ignites.
Now, black holes deserve a calm mention here, because they are a profound feedback engine. A supermassive black hole at the center of a galaxy can accrete gas. Accretion can power jets and winds. Those jets and winds can heat gas and prevent it from cooling. This can suppress star formation on large scales. So a black hole, which seems like a small central object compared to a whole galaxy, can influence the galaxy's long-term evolution. This is a feedback loop with enormous leverage, and leverage is often where sensitivity lives. If you change the feeding history of the black hole slightly, you can change the energy output, which changes the gas, which changes future feeding, which changes the galaxy. This is not chaos in the sense that anything can happen. It is chaos in the sense that complex outcomes can emerge from small variations. Now, you might ask, if the universe is so sensitive, how can we ever learn anything? The answer is by shifting the questions. Instead of asking, what will happen to this exact galaxy at this exact time, we ask, what are the typical outcomes for galaxies of this mass in this environment? Instead of asking, what is the exact shape of this filament in the future, we ask, how do filament statistics evolve with time? Science becomes a study of distributions, not micro-predictions. That is not a retreat. It is a deeper understanding of what prediction means. Now, let's bring this back to the phrase web of chaos. In a poetic sense, the cosmic web is a web of matter. In a scientific sense, the universe is also a web of interactions. Gravity coupling mass across space. Feedback coupling stars to gas. Black holes coupling central regions to whole galaxies. Each coupling can introduce sensitivity. So the web is not only spatial, it is causal. Now, to keep this restful, we can place another gentle image. Picture a filament of the cosmic web. Along the filament, gas streams toward a cluster. The gas is thin and glowing faintly. At the nodes where filaments intersect, shocks heat the gas. Within halos along the filament, galaxies form. Some galaxies produce winds. Winds enrich the filament with metals. Metals change cooling rates. Cooling changes star formation. Everything is connected by flows and feedback. Not in a way that makes the universe feel hostile, in a way that makes the universe feel alive. And now we can introduce a final calm idea that often appears in discussions of chaos: the difference between randomness and determinism. Randomness is unpredictability without a lawful cause, or with causes that are fundamentally probabilistic. Deterministic chaos is unpredictability arising from deterministic laws due to sensitivity. So in many cosmic systems, we have both: deterministic laws of gravity and fluid motion, plus genuine quantum randomness in certain microscopic events, plus practical randomness from unknown initial conditions. But on the largest scales, the universe still produces patterns. So we are not forced to choose between everything is predictable and everything is random. Reality is more nuanced. Now, in the next file, we'll talk about a place where chaos becomes deeply visual, the boundary of a cosmic structure, where voids meet filaments, where flows shear, where mixing happens. We'll also discuss how cosmologists quantify webness using topology and statistics without needing to predict every detail. If you're still awake, here is a calm question. When you hear feedback, do you picture regulation or amplification? Tell me in the comments what you intuitively imagine. Now, let's drift into the geometry of the cosmic web, the borders, the intersections, and the quiet mathematics of structure.
If you could see the cosmic web from far away, you might be tempted to call it a static sculpture, a net of filaments, a handful of bright clusters, large dark voids. But the web is not still. Matter is always streaming. Voids are not just empty, they are expanding regions with outflow. Filaments are not just lines, they are channels of infall. Clusters are not just knots, they are sinks, deep wells where matter collects and mixes. This motion is one reason the web resembles weather. There are flows, there are boundaries, there is shear, regions where flow speeds differ, creating instabilities. Where there is shear, there can be turbulence, not the same turbulence as inside a galaxy where the gas is dense and energetic, but a softer, larger-scale mixing. Shocks, ripples, waves propagating through a thin medium. Now, scientists have developed methods to characterize the cosmic web without needing to draw every filament by hand. They use statistics, correlation functions, power spectra, higher-order moments. They use topology, how structures connect, how many loops, how voids percolate. They use algorithms that detect filaments based on density gradients or the geometry of the gravitational potential. Each method yields a slightly different map, but the broad idea remains. The universe is a network with a characteristic texture. This is helpful because it lets us compare models to observations. If the universe were wildly chaotic in a way that erased statistical stability, such comparisons would be impossible. But they are possible, which means that the chaos, if present, is bounded. Now, there is another subtle point. The cosmic web is shaped mostly by gravity, and gravity is scale-free in a certain sense. It acts similarly across scales. But the universe also expands. Expansion changes the game. Expansion stretches distances and slows growth. In the early universe, when matter density was high, growth was faster. Later, as the universe expanded and as dark energy became dynamically important, growth slowed. So the web's evolution is not uniform in time. It has eras. This matters when we ask about predictability. If growth is faster in an era, small differences can amplify more quickly. If growth slows, amplification slows. So the chaos of structure formation can be time-dependent. Now, let's keep the tone gentle and introduce one more concept: attractors. In chaos theory, systems can have attractors, sets of states towards which the system tends to evolve. In simple systems, the attractor might be a fixed point or a stable cycle. In chaotic systems, it can be a strange attractor, a complex set in phase space that the system explores. The cosmic web is not usually described with attractors in the same way, because it is not a bounded dynamical system in a lab. But there is a related idea. Regardless of small-scale details, the large-scale distribution of matter tends towards certain statistical forms. For example, halos tend to have characteristic density profiles. The mass function of halos follows patterns.
The clustering of galaxies follows patterns. These are not exact attractors, but they are robust outcomes. They suggest that the universe has preferred statistical behaviors, given its initial conditions and laws. If you find that idea restful, you are not alone. It means that even if the details are complex, reality has habits. Now let's talk about the voids. Voids are among the most underappreciated structures in cosmology. They are large. They occupy most of the volume. They are not empty, but they are sparse. Voids expand faster than the average cosmic expansion, in a sense. Matter flows out of them towards filaments and nodes. If you imagine the web as a sponge, voids are the pores. Voids are also useful because they can be relatively clean environments. Less dense means fewer non-linear interactions. So in some ways, voids can preserve information about initial conditions more clearly than dense regions. Dense regions are mixed and stirred by mergers and feedback. Voids are quieter. This can create a paradox of predictability. The emptier a region is, the easier it can be to model. The denser and more active a region is, the more detail-sensitive it becomes. Now, we can connect this to a human feeling. In your own mind, some regions of thought are quiet and stable. Other regions are dense and active. In the quiet regions, it is easier to see patterns. In the dense regions, it is easier to feel overwhelmed by detail. The universe has voids and knots. So do we. Now, how do we move from this web description back to chaos in a more technical way? One path is to examine how small perturbations propagate through gravitational collapse. In n-body simulations, you can perturb initial conditions slightly and examine how the divergence grows. You can measure something like a Lyapunov exponent for the system, though in a cosmological context, it is more complicated because of expansion and large-scale constraints. The emerging result is subtle. The system can be sensitive, but that sensitivity is not uniform. Some scales and environments are more sensitive than others. Dense halo centers are highly nonlinear and sensitive. Large-scale modes are more stable. So the web is a layered system, and layers are exactly what we need for a calm narrative. We can acknowledge sensitivity without making the whole universe sound unstable. Now, in the next file, we'll take a slightly more philosophical turn. We'll talk about what chaos means for scientific prediction, why knowing the laws is not the same as knowing the future. And we'll also talk about why this doesn't weaken science, but makes it more honest and more powerful. If you are still awake, here is a gentle question. When you look at a complex pattern, clouds, waves, branches, do you feel more comforted by the idea that it has rules, or more fascinated by the idea that it has freedom? Share your thought in the comments if you like. Now, let's move into the meaning of prediction itself, the quiet boundary between knowledge and forecast.
Prediction is one of the most human instincts. We predict the weather, we predict traffic, we predict a friend's mood, we predict the next scene in a story. And in science, prediction is often treated as the gold standard. A theory is valuable if it can forecast what we will observe. But chaos teaches a careful lesson. A theory can be perfectly correct and still not allow long-term detailed prediction. This is not because the theory is weak, it is because the system is sensitive. So prediction becomes a layered concept. On short timescales, you can predict details. On longer timescales, you predict distributions.
On very long timescales, you predict qualitative regimes. Weather is the classic example. We can forecast a few days with detail. We can forecast seasons with statistics. We cannot forecast the exact pattern of clouds weeks in advance. And yet, meteorology is not a failure. It is a triumph. It is a science that learned to match its questions to the structure of reality. Cosmology is similar. We can predict the distribution of matter statistically. We can predict how structures grow on average. We can predict how many clusters of a given mass should exist. We can predict patterns in the cosmic microwave background. We can predict lensing statistics. But predicting the exact merger history of one particular galaxy billions of years from now is not the goal. Now, there is a quiet psychological shift here. Many people grow up with the idea that if you know enough, you can control enough. Chaos does not deny knowledge, but it does soften the fantasy of total control. It says, there are limits that are not personal. There are limits that are structural. And that can be soothing, because it means you do not have to blame yourself for every uncertainty. Some uncertainty is part of how complex systems breathe. Now, let's connect this to the idea of the cosmic web as a web of chaos. The cosmic web contains both stability and sensitivity. Stability in the sense that its statistical texture is robust. Sensitivity in the sense that local details, small halos, substructure, gas flows, can vary dramatically with small differences. So the cosmos is not a fixed blueprint. It is a range of possible realizations. Our universe is one realization, and in cosmology, that fact has a name: cosmic variance. Cosmic variance is the idea that we have one universe to observe, one sky to measure. On large scales, there are only a few independent samples. So even if we had perfect instruments, there would be statistical uncertainty simply because we have one realization. This is a different kind of limit than chaos, but it feels related. Both tell us that some uncertainty is fundamental to the situation, not to our competence. Now, if you're listening late, you can let that idea be gentle. You can think of the universe as a single tapestry. We can examine it closely, but we cannot compare it to 1,000 other tapestries drawn from the same loom. We can, however, simulate other tapestries, and that is how we build confidence in our models. Simulations are like alternate universes we can run on a computer, not to replace reality, but to explore the space of outcomes allowed by the laws. When a model consistently produces patterns like the one we observe, we gain trust. When it fails, we learn what needs to change. Now, a soft warning. Simulations can never capture everything. They approximate. They model feedback with effective rules. They have finite resolution, but they are still invaluable because they show us how structure emerges from interaction. They show us that a web can be built from gravity, and they show us that the chaos is not the enemy of understanding. It is part of the explanation. Now, let's revisit a simple phrase: sensitive dependence on initial conditions. This phrase can sound technical, but it points to a universal experience. If you slightly change the start of a story, the end can change. If you slightly change the angle of a ball, the bounce changes. If you slightly change the temperature of air, storms can develop differently. In the cosmos, the initial conditions are the early density fluctuations. They were small, but they were the seeds, and seeds matter. This also gives a new appreciation for the early universe. The early universe was not only simple, it was decisive. Tiny differences in that era echo forward into the distribution of galaxies today. This is not spooky, it is causal. Now we can ask a quiet question. If tiny differences can matter so much, does that make the universe feel fragile, or does it make it feel creative? Because sensitivity can be seen in two ways, as a loss of certainty or as a source of variety. Nature has chosen variety. Now, we're approaching the closing part of this episode. We have spoken about chaos as sensitivity, orbits as gentle long-term unpredictability, the cosmic web as emergent structure, turbulence and feedback as sources of complexity, prediction as a layered concept. In the final 3 files, we'll slow down and let these ideas become more meditative. We'll return to the web itself, the visual pattern of filaments and voids, and we'll treat it as a calm metaphor, a reminder that complexity can still be coherent. If you are still awake, you can answer one more question for engagement. Do you find it comforting that the universe has limits to prediction, or do you prefer the idea of a cosmos that is fully forecastable? Comment below with your honest instinct. Now, let's ease into the final movement, a quieter view of the web.
Let's return to the web, but now not as a concept to analyze, as a scene. Imagine floating far above the galaxies, high enough that individual stars blur into glow. Below you, the universe looks like a misty network, bright nodes where clusters live, long filaments connecting them, faint and thread-like, wide dark spaces between, where voids expand and matter is sparse. Nothing rushes, everything moves, but on timescales too long to feel. It is a slow river of gravity. If you drift closer to a filament, you might see that it is not a single rope, but many strands, halos, groups of galaxies, small bridges of gas, subtle streams. The filament is not perfectly smooth. It has texture. This texture is the result of many histories, many infalls, many mergers. If you could rewind time, you would see the filament unweave and then reweave differently, depending on tiny differences in the beginning. That is the quiet chaos, not the existence of the filament, but the precise way it is braided. Now, imagine a void, a region where galaxies are few, gas is thin, light is dim. Voids are not empty, they are simply unburdened. Matter flows outward from them toward the filaments. In that sense, a void is a gentle source, and the filament is a gentle sink. If you want, you can treat that as a calming metaphor. Some parts of the mind are void-like, open space where thoughts can expand and disperse. Other parts are filament-like, channels where attention flows and concentrates. Both are necessary. Both shape the whole. Now, in chaos theory, there is a concept called mixing. Mixing is what happens when trajectories stretch and fold.
It is what makes a system forget its initial fine details, even though it remains lawful. In the cosmos, mixing happens in halos. Matter falls in, it orbits, it merges, it relaxes. After enough mixing, the halo's memory of exact initial positions is lost, but the halo's statistical properties remain. This is why, if you look at a cluster of galaxies, it can appear stable even though it was built through countless complex interactions. Stability can be emergent. It can be the result of mixing, not the absence of motion. Now, there is a soft irony here. Chaos to many people means disorder, but in many systems, chaos is part of how order emerges. Instability creates structure. Mixing creates equilibrium. Feedback creates regulation. The web is the child of instability. The calm, large-scale structure is the end product of many sensitive processes. So the universe is not fighting chaos, it is using it. Now we can pause with a gentle reflection. Sometimes when life feels chaotic, the instinct is to demand control, to force everything into a perfect forecast. But the universe suggests a different approach, to look for patterns that are stable in statistics, not in details, to hold a steady direction, even if the exact path varies, to accept that variability is not failure, it is reality. Now, if you are still awake, here's a quiet engagement question that fits this moment. When you hear the phrase web of chaos, what image comes to your mind? Is it a cosmic network? Is it a mind map of connected thoughts? Is it a storm pattern? Is it something else? Tell me in the comments. I genuinely use those answers to shape the visuals and pacing in future episodes. Now, we're almost done. In the last 2 files, we'll become even slower. We'll summarize without pressure. We'll close with a gentle goodnight and a subtle invitation to subscribe without breaking the mood. Let's move toward that closing now. Before we do, let's rest for a moment on one more quiet detail. When cosmologists talk about the web, they often emphasize that it is not drawn by hand, it is not designed, it emerges. And emergence is one of the most calming ideas in science. It means that complex patterns can arise without a planner, simply from many simple interactions repeated over time. Gravity pulls, expansion stretches, matter flows. From those ingredients, a network appears. If you watch a simulation, the web does not appear instantly. It slowly clarifies. Over time, faint threads strengthen. Nodes become brighter. Voids grow emptier. It's like watching a photograph develop in a dark room, very slowly. And if you look closely, you'll notice something soothing. The web does not need to be perfect to be beautiful. Filaments are not straight. Nodes are not symmetrical. Voids are not identical. The universe seems comfortable with irregularity. That irregularity is not a flaw. It is the signature of history. Every bend is a memory of a merger. Every thickening is a record of infall. Every thin strand is a path matter took when it had other choices. If you let yourself imagine a calm camera drifting along a filament, you can almost feel that history as layers of motion. Not loud motion, slow motion. The kind of motion that becomes invisible unless you wait. If you take this episode in one hand and hold it gently, it becomes simple. Chaos is not noise. Chaos is sensitivity. The laws can be steady. The outcomes can still vary. The solar system can be stable for billions of years and still have long-term unpredictability in its fine details. A galaxy can have a recognizable shape and still contain turbulent gas that is impossible to predict exactly. The cosmic web can have a robust statistical texture and still braid itself in different ways with tiny changes. So the universe contains both order and freedom, structure and variation. And perhaps that combination is why it feels so deep. Now, if you are listening at night, you can let the technical words fall away. You do not need Lyapunov or phase space. You can keep only the feeling that complexity can be lawful. If you want, you can do one more calming visualization. Imagine a point of light. Now imagine many points of light. Now imagine threads connecting them, faint and soft. The threads are the filaments, the points are the clusters, the spaces between are voids. Everything moves, but nothing hurries. And inside the motion, small differences matter. That is all. Now, there is one more lesson hidden here, and it is quiet but important. Chaos does not destroy meaning. It changes what meaning looks like. Meaning becomes statistical. Meaning becomes pattern. Meaning becomes the way the whole behaves, not the exact fate of every piece. In science, that is how we learn to respect complex systems. In life, it can be how we learn to respect our own limits. Now, if you are still awake and you want to share something, have you ever experienced a moment where a tiny change led to a very different outcome? Not in a dramatic movie way, in a real, ordinary way. A missed train, a different conversation, a small decision. If that resonates, you are touching the same principle chaos theory describes, just in human scale. And it can be soothing because it means the future is not a single rigid line. It is a field of possible paths. Now, one last gentle clarification. Chaos does not mean anything can happen. In a chaotic system, outcomes are still constrained. There are boundaries, there are tendencies, there are attractors or statistical habits. So the universe remains disciplined. It does not dissolve into randomness. And that discipline is what makes astronomy possible. We can measure, we can model, we can predict enough to learn, even when we cannot predict everything. Now, in the final file, we'll close softly. We'll offer a quiet call to action, the way a whisper invites, not demands. And we'll let the web dissolve back into darkness. And if you want one more gentle idea to carry with you, it is this. Chaos can coexist with stability. A coastline is irregular, but the ocean is still the ocean. A flame flickers, but the candle remains. A cloud changes shape, but the sky stays quiet. In the same way, the universe can be dynamic without being frantic. It can be sensitive without being fragile. Sometimes when people hear about chaos, they imagine a loss of ground. But in science, chaos often means the opposite. It means we have found the underlying rules, and now we are confronting their full richness. Even the limits are informative. They tell us what kinds of questions reality can answer cleanly and what kinds of questions it answers only in averages. So if uncertainty shows up in your life, small changes, shifting outcomes, you can remember that nature itself is built this way. It is not personal, it is not moral, it is structural. And in that sense, the web of chaos is not something to fight. It is something to understand and then to move within gently. One more quiet angle before we end. In cosmology, there is a reason researchers love large surveys. The more galaxies you observe, the more the small irregularities average out. You begin to see the underlying pattern with clarity. This is a scientific strategy for living with chaos. Do not demand certainty from a single point. Collect enough context that the pattern becomes visible. In your own life, a single day can feel noisy. A single conversation can feel confusing. But a longer view, a month, a year, often reveals what was consistent all along. The universe teaches that lesson with its web. Individual filaments are irregular, but the whole network has a recognizable texture. So tonight, you can give yourself permission to release the need to predict every detail. You can choose instead to trust the larger pattern. And if you want a small practice, notice one stable thing about your day, even a tiny one. Then let the rest blur softly, the way distant galaxies blur into glow.
As we close, let's return to a single calm sentence. The universe can be lawful and still not be fully predictable. That sentence is not a limitation. It is a description of depth. Because depth means there is room for variation, room for surprise, room for complexity that does not break the rules. Tonight, we moved from the solar system, where tiny gravitational tugs accumulate over millions of years, to the cosmic web, where gravity amplifies small fluctuations into filaments and voids, to the inner life of galaxies, where turbulence and feedback create intricate, sensitive patterns. And we saw that the same principle appears in different forms. Sensitivity does not ruin the universe, it shapes it. Now, if you want to carry one image into sleep, let it be the web, a network of dim threads across a dark ocean, a slow river of gravity, a structure made from tiny beginnings stretched across time. And inside that web, the details are endlessly rich, but the whole remains calm. If you enjoyed this episode and you'd like more sleep-friendly cosmic documentaries, calm, quiet, and gently curious, you can support the channel in a simple way. You can like the video so it reaches more listeners who want peaceful science at night. You can subscribe so you don't miss the next episode. And if you know someone who sleeps best with quiet space stories, you can share this with them. No pressure, just a quiet invitation. In future episodes, we'll explore more of the universe's subtle edges, the behavior of voids, the strange chemistry of distant atmospheres, the new instruments that keep changing what known means. For now, you can let the web fade. Let the filaments soften into darkness. Let the clusters dim into quiet points. Let the voids expand into calm space. One slow breath in, one slow breath out. And if a thought arrives, you can treat it like a distant galaxy, real but far away, passing gently through your attention. If you want a simple closing image, picture this: a single filament of the cosmic web, dim and delicate. Along it, galaxies glow like tiny embers. Between them, darkness, not emptiness, just quiet space. Now picture that filament joining another and another. A network forms, not a trap, a map. And in that map, everything is moving, but the movement is slow enough to feel like stillness. That is the kind of calm the universe offers. Not the calm of nothing happening, the calm of motion that is patient. If you found this episode helpful for sleep, you can also let me know what pacing works best for you. Do you prefer longer holds and fewer concepts, or slightly more variety with the same gentle tone? Your feedback helps shape future episodes for the US and UK audience who listen at night. Thank you for being here. And one final reminder, whispered rather than announced: you do not have to solve the universe to feel its calm. You only have to notice that it is vast and that it continues quietly, regardless of the day you had. Let the web hold the night for you. Let the idea of lawful complexity take some weight off your mind. Let uncertainty be part of the landscape, not an emergency. Sometimes people think calm requires certainty, but the sky suggests another form of calm, the calm of accepting complexity without fear. In a chaotic system, you can still have boundaries, you can still have tendencies, you can still have steady laws. So you can rest, not because everything is known, but because everything is held by structure. Now the web can fade again. Filaments dissolve, clusters dim, voids expand into quiet space. If you're still awake, you can let your attention settle on something simple: the weight of your body, the softness of the room, the steady rhythm of breathing. And if sleep arrives, let it arrive naturally, like gravity, gentle and patient. And if you want to stay with the science a little longer, here is a final quiet thought. The most powerful predictions in cosmology are not about a single object. They are about the shape of possibility. They tell us what kinds of structures should exist. They tell us how common certain environments should be. They tell us how the web should thicken and thin over time. That is enough. Enough to guide telescopes, enough to interpret what we see, enough to keep wonder disciplined and calm. And now we can truly end. The universe continues outside the window, quietly weaving and unweaving its patterns. You don't have to follow every thread. You can simply rest. And if you return tomorrow night, the web will still be there, waiting in the dark, patient and immense, a calm reminder that complexity can be kind. Good night.